Today we're going to look at a quick review of different ways to factor polynomial expressions completely. So we're going to start out with the first type of factoring that you are taught when you're looking at ways to factor expressions, and that's the greatest common factor. Remember, a greatest common factor is a monomial that will divide evenly into every single term, and it's the largest monomial that will divide evenly into each term. As you're looking for the greatest common factor, it's always a good idea to look at your terms and then find the term with the smallest leading coefficient, because then the largest factor that divides into this will not give you a whole big list as if the factors that would divide into 54. So when I think of factors that divide into 24, factors of 24, I can use 1 and 24, which those won't match there, 2 or 12, 2 works, but I don't know if that's the biggest one. 3 and 8, and then 4, 6. Now, if I think about all those lists of factors, 6 is the biggest number out of that list that will also divide into 54. So in terms of my monomial, I'm going to use 6. And then when it comes to variables, you always want to, if they have the same variable, choose the variable with the lower exponent, and that's going to be your common factor for that. So for 24x to the fourth minus 54x cubed, my largest common factor is going to be 6x cubed. And then in parentheses, what we do is we write the remaining factors. In other words, the value that would be left if we divide each term by that. So if I take 24x to the fourth and divide it by 6x cubed, 24 divided by 6 is 4. And then x to the fourth divided by x cubed is 1x. So I'm going to get 4x. Here I have a negative 54x cubed with a positive 6x cubed. So if I take negative 54x cubed and divide it by positive, I'm going to get a negative 9. So I'm going to write that in my parentheses as minus 9. And that's how we factor out the greatest common factor here. Let's look at one more example. When I'm looking at these two terms, 17 is the smaller value. 17 is prime. I can only divide by 1 or 17, and it just so happens that 51 does divide evenly by 17. So I'm going to factor that out as the common factor. And then I can see that both have values of a, so I'm going to take the lower exponent, a cubed. And they both have values of b, so I'm going to take out the lower exponent of b fourth. So there's my GCF. And then in parentheses, again, I'm going to write what's left behind as I divide each term by that. So 51 a to the 8th b to the 4th divided by 17 a cubed b to the 4th will give me 3 a to the 5th and no more b's. So just 3 a to the 5th if I divide that out. A positive divided by a positive stays positive. 17 divided by 17 is 1. You can obviously write the 1 if you want. But I'm going to be left with some more terms, so I'm not going to bother writing the 1. The a cubes all disappear. B to the 5th divided by b to the 4th is b. So that's where I'm factoring out a greatest common factor. Now, as we go through and look at some factoring techniques, we might see that we might have to then take out a common factor and then use other factoring techniques with what's left behind. But these two expressions that were left behind are prime, so these problems would be finished. The next type of factoring that you looked at was factoring different types of trinomials. And when you're factoring trinomials, either you have a leading coefficient of 1 or a leading coefficient that's not 1. And we can use the same strategy regardless of whether the leading coefficient is 1 or not. We can use what's known as guess and check. Or we can look at a factoring by grouping technique, which is what we'll look at for one of these examples down here. But when we're trying to use guess and check, especially when the leading coefficient is 1, what's going to happen is we're going to make two groups. So we can create two binomials that will multiply together. And we're going to look at the first term, and we're going to try to think about what numbers or values would multiply to make m squared. Now, m squared can only be created by taking m times m. Now we go to the last term, and my last term is negative 30. Now, if I think of ways to multiply to make 30, I can use 1 times 30, 2 times 15, 3 times 10, 5 times 6, And I want to find the factors that are going to multiply to make a negative 30. So that means I need one of these to be a positive and one of these to be a negative. And at the same time, they have to add to give me that middle term. So that they add to give me negative 13. So if I'm looking at my list and I want one number to be positive and one number to be negative and give me a negative 13, this is the group that's going to do that for me. If I take a positive 2 times a negative 15, I get negative 30. And if I take 2 minus 15, I get that negative 13. So these are the two factors that I'm going to finish up my groups with. I'm going to put a positive 2 in one group and a negative 15 in the other. And that's my guess and check strategy here. Now, when the last number is positive, as in example 4 here, when the last number is positive, the way to multiply two numbers to make a positive 15 is either to take a positive times a positive or a negative times a negative. And what we do is we look at that middle term, and that's going to help us decide. The only way I'm going to get this to be a negative and this to be positive if I multiply two negative numbers together. So I want numbers that multiply to make 15, but add to give me a negative 8. So if I think about that, I'm going to get my x. Numbers that multiply to make positive 15 but add to give me negative 8 would be negative 3 and negative 5. Now, I can use the same guess and check strategy even when my leading coefficient is not 1. So let's look at this example and look at how I would use guess and check with this strategy. I basically start out the same way with my two groups. I look at my first term and I think of ways that I can multiply to make 2d squared. So the only way I can multiply numbers to make 2 would be 2 times 1, and then d squared would become d times d. So I'm going to put a 2d in one group and a 1d in another group, or just d. Now, same thing. I'm going to look at my last number, and I want numbers that multiply to make negative 7. Now, numbers that multiply to make negative 7 would either be negative 1 times 7 or 1 times negative 7. There's no other list of values for that. 7 was a prime value there. So I have to decide whether I want to put 1, 7 or 7, 1. So I always kind of look at what my middle number is. And in this case, it's negative 13. So I know that I need to make 2 kind of grow pretty big. So I'm going to put the 7 over here, and that way my outer factors are coming together to give me 14d. And then if I put the 1 there, my inner factors are coming together to give me 1d. And if I want to combine these together to get negative 13, then that guy needed to be the negative. So if that's the case, I look at this. This would be my negative 7, and this would be my positive 1. And now that was the guess and check strategy. If guess and check strategy gives you a hard time, you can always convert any trinomial into 4 terms and use a factor by grouping technique, which would take this middle term and separate it up into 2 separate values that would add up together to give you that. And we want to make sure we pick the right values that are going to allow factoring by grouping to work. So if we're going to convert this to 4 terms, the first thing we'll do is multiply the first and the last term together. So I'm going to take 10x squared times 9. That gives me 90x squared. Now I want to think about numbers that are going to multiply to make 90, but add to give me a negative 21. Now again, this is a positive 90. So when I'm thinking about numbers that add to give me negative 21, the only way this is going to become positive and this is going to be negative is by having 2 negative values, similar to this situation up here. So I can do negative 1x times negative 90x, but no, that's not going to be negative 21. I can do negative 2x with negative 45x. Nope. I can do negative 3x with negative 30x. I can do, let's see, negative 5x with negative 18x. Getting close, but not quite. And then I can also do negative 6x with negative 15x. And if I multiply that, negative 6 times negative 15 gives me that 90. There's my x squared. If I add them, that's that. So what I'm going to do now is replace that middle term with both of those. So I'm going to split up negative 21x into those two parts. And once I split it up into these four terms, now I'm going to use that factoring by grouping technique. And in factoring by grouping, you look at each part of that polynomial, you break it up into two pieces. So we're going to look at the first two terms and find a GCF, and then we're going to look at the last two terms and find their GCF. So between 10x squared and 6x, the largest common factor would be a positive 2x. And if I divide them out, I'm going to get 5x minus 3. And then in the second half of the problem, when I have negative 15x and positive 9, if your first term is negative, you're going to factor out a negative GCF. So I'm going to factor out a negative, and between these two terms, the largest value that would divide into them would be 3. So I'm going to factor out a negative 3. If I divide this by negative 3, I get positive 5x. If I divide that by negative 3, I get negative 3. You know factoring by grouping is going your way if these two terms match, because now that's your common factor. But instead of being a monomial factor, it's a binomial factor. So what I'm going to do now is take this out as a common factor, and then in parentheses, I'm going to put the remaining. So if I factor that out from here, I'm left with 2x. And if I factor it out from there, I'm left with minus 3. And that's how I could do a factor by grouping technique when my leading coefficient is not 1. The last type of factoring we're going to look at is when we have factoring four terms. And then we're going to look at some special scenarios for factoring. So when we have four terms, obviously we're not going to be able to use the strategies we used here, but we can use the strategy we looked at in this set right here once I took it from a trinomial and made it four terms. When we have four terms, we're going to break it up and try factoring by grouping. So we're going to split it up into two parts and look for the GCF in each part. So in this first group, my GCF would be just h squared. And then I'd be left with 2h minus 3. In the second group, between 6h and 9, my GCF would be 3. And it's going to be a positive 3 because my leading coefficient in that group was positive. And if I divide that out, I'm going to be left with 2h minus 3 when I divide both of those terms by that 3. Once again, I know factoring by grouping is working because I now have that common binomial factor. So I'm going to factor out from each group there that 2h minus 3. And in parentheses, I'm going to write the remaining factor here, which would be h squared, and then the remaining factor here, which would be positive 3. And then one more example of our factoring by grouping. In this case here, the first two terms, the common factor would be x squared. And then in parentheses, I would be left with x plus 7 if I divide them both by x squared. Here again, since the first term is negative in this group, I'm going to factor out a negative. And between these two terms, I'm going to factor out that 5. So negative 5. If I divide this by negative 5, I'm left with positive x. And if I divide this by negative 5, I'm left with positive 7. There's my common binomial factor. And then I'm going to put those remaining factors in that group there. So that's how we use our basic factoring techniques for trinomials and these polynomials with four terms. We're going to wrap up some factoring techniques by looking at some binomials and looking at some special factoring patterns with binomials or two terms. One of the factoring patterns we have with two terms is known as the difference of two squares. And in a difference of two squares factoring pattern, what's going to happen is we're going to have two perfect squares that are subtracting. So the rule looks like x squared minus y squared. So what we do to factor that is, if you notice, there's no middle term. So that meant that when we did our foiling or multiplied these two binomials together, the outers and the inners canceled out. So that means that they had to have the same product in the inner terms as they did with the outer terms. They just had to be opposite signs to cancel. So that means that I took the square root of the first term, and that became my first term in each group. And I took the square root of the last term, and that became the last term in each group. And then to guarantee that I had a negative, one of them had to be positive and one of them had to be negative. And up here, I just gave you a list of some of the perfect squares from 1 to 10. So if I look here, 36x squared minus 25. This is a perfect square. It's 6x times 6x. And this is a perfect square. It's 5 times 5. And they have that minus sign in between. So when I go ahead to factor this as a difference of two squares, I'm going to take this and break it up as 6x times 6x. And take that 25, break it up as 5 times 5. And because this was a negative 25, I need a positive and a negative. And that's my difference of two squares pattern. Just be careful. When you're looking at a difference of two squares, it has to be a difference. So that means it has to be subtraction. Because once I change this to a plus sign, the only way to make a positive number at the end here is either to multiply by a positive times a positive or a negative times a negative. And if I have both positives or both negatives, the inner term will never cancel out. So even though this is a perfect square, and even though that's a perfect square, because this is not a minus sign, I cannot factor this. And we would just say that this example is prime. The other type of special binomials we have is when we have a sum or a difference of two cubes. Now, I gave you a list of perfect cubes from 1 through 10 there, so that's a good idea to look at. And the rules look very similar whether it's a sum or a difference. The main thing is that when it's a sum, you put x plus y. When it's a difference, you put x minus y. These two, notice that the groups here and here look exactly the same, but the big difference is that in this group, when it's a sum of two cubes, the first one is minus, and when it's a difference of two cubes, the first term here is a plus. The last one is always positive. So something that we're taught to help us remember how to factor is SOAP. So when you're factoring a sum or a difference of two cubes, in your first group, your sign here is the same. So when it's a sum, it's the same. When it's a minus, it's a minus. Then it's opposite. So notice that this went from a plus sign to a minus. That went from a minus to a plus. And then the last one is always positive. That's what the AP stands for. So same, opposite, always positive, SOAP. And that's how you can help you remember whether you should be using, what signs you should be using. Other than that, how you build the polynomials that are being multiplied together is exactly the same. When we're factoring a sum or a difference of two cubes, we have to make sure that these are both perfect cubes. So h cubed, the cube root would be h. 125, the cube root would be 5. So that's what this part tells me. It says x plus y. These stands for the cube roots of the first term, cube root of the last term. So h and 5, and then it's the same sign there, so plus. Now here it's telling you to take whatever that cube root was and square it. So whatever value you put in your parentheses first here, you're going to square that. So this is going to become h squared. Then I do the opposite sign. Now notice it's saying multiply x times y. What that's telling me to do is multiply the cube roots together. So I'm going to look at these two, and I'm multiplying them together. h times 5 would be 5h. And then it's always positive at the end. And then you take the last term that you created, that cube root, and you square it. So 5 squared would be 25. All right, let's look at that again. So for this one right here, the cube root of 8f cubed would be 2f. The cube root of 27 would be 3. I'm going to keep the same sign. And now I take the first term here and I square it. Put a minus sign for the opposite. I multiply these two together, so 2f times 3 would be 6f. Always positive, and then take that last term there and square it. Okay? Now again, it's the same thing whether it's a sum or a difference of two cubes. The only thing that's going to change in terms of the pattern are the signs. So when I go to factor x cubed minus 343, 343 is in my list. I can see that it's right there. That's 7 cubed. So this is a perfect cube. The cube root of that would be x. The cube root of that would be 7. So I'm going to start out with x minus 7. So I keep the same sign as the original problem. Then once I have the two cube roots, I look at the first one and I square it. Then I do the opposite sign. I multiply these two terms together, so x times 7, so 7x. And then I look at the last term and I square it, so 49. And remember, it's always positive at the end. All right, one more example. The cube root of 125 is 5. I'm going to keep my same sign. The cube root of 8x cubed would be 2x. So those are my two cubes. That's my x and my y. Now I do, for my first term, x squared. So I take the first term and square it. I'm going to do the opposite sign of the original problem. Multiply those two terms together. So 5 times 2x is 10x. Last term is always positive. And then I'm going to square that. So 2x times 2x would give me 4x squared. So those are our factoring patterns for our sum and difference of two cubes. And then we're going to wrap up by just combining everything together. So when we're looking at factoring, you want to always make sure, a lot of times your directions will say factor completely. So you always want to check for a GCF first, especially when that leading coefficient is not 1. It's possible that that GCF will factor out and then make your whole life a lot easier. So always, always, always when we're factoring, check for a GCF first. And if it's a trinomial, or if it has 4 terms, you always want to make sure it's a common factor of every single term. So it has to divide into everybody that's at that party there. So when I'm looking at this polynomial, I have to make sure that the value I choose divides into both 6x squared, 14x, and 4. And I always start by looking at the smallest number and find the factors for there. So the largest factor of 4 that's going to divide into everybody here is going to be 2. And since my leading coefficient is negative, I'm going to factor out a negative. So my GCF is going to start out with negative 2. Now, even though these both have x's, since this one doesn't have an x in it, I can't factor out an x from everybody, so I'm not going to factor out an x term. So I'm just going to factor out negative 2. And in parentheses, I'm going to write what's left as I factor each term by that. So if I take negative 6x squared divided by negative 2, I'm going to be left with positive 3x squared. If I take negative 14x and divide it by negative 2, I'm left with a positive 7x. And if I take negative 4 and divide it by negative 2, I'm left with a positive 2. Once you factor out your GCF, you should always be looking at your remaining polynomial and seeing if it can factor more. In every example I've done before, they've always been prime, and there was nowhere else we could go with these problems. But you should always check to make sure that these can't be factored more. So I want to look at this trinomial and see if I can factor it as 2 binomial parts using my techniques that we looked at on the front side. When you're factoring, always make sure that you carry that GCF from one step to the next. Because without that GCF, if you drop it halfway through the problem, you'll never be able to create the original function back. And we always want to create expressions that are equivalent to what we started with. So I have to carry around that negative 2. But now as I finish up the problem, I'm going to focus only on that trinomial. So I have a quadratic. So I want to see if I can factor this. Now I could do grouping, but I'm just going to do guess and check. Because 3x squared can only be created by taking 3x times x. So looking at that first term, I don't have a lot of options. And same thing with 2. I can really only make 2 by multiplying 1 times 2 or 2 times 1. So I have to decide whether I want to put 1 and 2 or 2 and 1. Since I want to get a 7, I want the larger value with that 3. So I'm going to put the 2 there and the 1 there. Both signs here were positive, so that means I need 2 positives to make the positive 2, and that'll give me 2 positive terms to add to give me a positive 7. If I do a quick check of my inner and my outer terms, I can see that yes, together, these will add up to give me that positive 7x in the middle that I want. So this would be my final answer for that problem. And then in this last binomial, I can see that they both have a common factor of 5. And this time, both terms have an n. So I'm going to also factor out that n. In this group, that's going to leave me with n to the 4th. I'm going to keep that minus sign. If I take 180n divided by 5n, I'm going to be left with 36. I have a binomial with a minus sign. This is a perfect square because n squared times n squared will give me n to the 4th. This is a perfect square. 6 times 6 will give me 36. So I'm going to go ahead and now factor this new expression by using that difference of two squares technique. And again, I'm going to keep that 5n, and then I'm going to factor my difference of two squares. And notice I created two more binomials. This one has a plus sign, so I can't do anything. I should really be checking this. That's a perfect square, but this one's not. So if this had been 9 or 81 or 36, I would keep on factoring. But because this is n squared minus 6, and this is a perfect square, but this one's not, I'm finished. So just remember, always check for a GCF first, and then after you factor out a GCF, use any of your factoring strategies that we've looked at earlier. And as we're moving forward through the course, we're going to see how we're going to use these factoring strategies with other expressions and other functions, not just with our variables like x's and n's and y's. All right, let me know if you have any questions.